All right, so to finish where we left off, which we kind of need this because we're actually going to answer this question in the next section of this. So we have two towers that are 30 feet apart. Okay, so we have tower one. One tower is 12 feet and another tower is 28 feet. So we have here our 12-foot tower and our 28-foot tower. And there's 30 feet in between. Okay. Now, in between each tower, there is a stake in the ground, and the top of each tower is a wire tied that connects it to the stake. So somewhere in between, we have a wire between the two. Okay. What we want to do is we want to minimize the amount of wire. Okay. So here we have wire one and wire two. Okay. We want to minimize that amount of wire. Now, we don't know, what we want to do is we want to know where do we put the stake in between the two that will minimize that value. Okay. We do know that there's 30 feet in between. Okay. So where do we put the stake? Well, the idea here is we're going to put one of these distances to the stake as x, which makes the other one 30 minus x. And if I want to find the value of W1, wire 1, and wire 2, well, again, that's our favorite theorem ever. So wire 1 is equal to the square root of 28 squared plus 30 minus x squared. And then wire 2 is equal to the square root of 12 squared plus x squared. And the idea here is that the total length would be the sum of these two. So the wire is equal to 28 squared plus 30 plus x squared plus 12 squared plus x squared. Now we actually don't have to do anything else. That puts our function we want to find or use to find the minimum value, and we have everything in terms of one variable, x. So we are going to finish this, and we're actually going to finish some of the questions we started yesterday, starting with this one here. We stated that the distance formula was square root specifically for this case, x minus 5 squared plus x squared, which we simplified to be the square root of x squared minus 9x plus 25. All right, so the idea here is in order to find the min or max value, we are going to take the derivative, so d prime would be 2 square root of x squared minus 9x plus 25. And then the derivative of what's inside would be 2x minus 9. I think we've done enough square root derivatives to know that that's the way it's going to end up being. If not, then I would go practice some more. Okay. But yeah, basically we just bring down the 1/2. It's going to go into the denominator because you now have a negative 1/2 exponent. So yeah. And then the chain. Now, the nice thing about this is in order to find the maximum value, all we are going to do is we are going to set this equal to 0. And when is a fraction equal to 0? So we just set the numerator equal to 0. 2x minus 9 equals 0, which means x is equal to 4.5. Right? Which means, if you want to list this as a fraction, x equals 9 over 2, that might actually be better. Because if you want the actual coordinate, we need to plug that back into the function. Y is equal to the square root of 9 over 2, which is 3 over root 2. So my coordinate that is closest to 5, 0 on this graph is 9 over 2, 3 over root 2. To the tower, okay, where we said that the y is equal to the square root. Let's keep that a little better there. Of 28 squared plus 30 minus x squared plus the square root of 12 squared plus x squared. The derivative of that is a little more fun. So again, we can do these separate. We do know that this is going to be what 2 square root of 28 squared plus 30 minus x squared over, again, the derivative of 28 is 0. So that is 2 30 minus x times a negative 1 if you do the chain within the chain. Plus 2 squared of 12 squared plus x squared over 2x. Now we can simplify this a little bit because we have the 2 here and here, here and here. And we can distribute and make this x minus 30 over the square root of 28 squared plus 30 minus x squared plus x over square root of 12 squared plus x squared. Now, we're not going to do this by hand. Okay, we are going to get out our calculator. And I have already put it in my graphing calculator because I did this last night. So put it on there. Again, you should know at this point how to find an x-intercept. Okay, so you put this in your calculator, you graph it. My graphing calculator is a little bit different because it's not a TI app. So I can just press intersect, or sorry, root, and it tells me that my root is 9. So x equals 9. Now in this case, they want to know 9 feet. Okay, so do make sure you do put the units involved. So 9 feet. Okay. Now, what that means in context, since we said back in our previous question that x is the distance from the shorter tower. So you may have to phrase it specifically that x is 9 feet from the 12-foot tower and 21 feet from the 28-foot tower. So I don't know how they want you to phrase that in this case. So you could say the stake should be 9 feet from the shorter tower. So we do optimization quite a bit. So I know when we have running, like one question that comes to mind quite a bit is we had this question that's like we run a wire parallel to a river, okay, and when I'm above ground, when I'm parallel to the river, it costs this much to run this wire. But when I have to put it across the river, it has to be dug underground. It's a lot more money to place it there. So we have to figure out where should I start. Okay, what location should I start digging underground to minimize the cost of putting this wire up? So stuff like that happens. I think that was one of the business calc questions we had. So it was a really fun question. A particle is traveling along the x-axis. Its position from the origin can be modeled by this function. So this is back to that velocity acceleration. So on the interval from 3 to 9, find when the particle is moving fastest to the right. So fastest again would be the max velocity. Okay, so we do need the velocity function. V of t is equal to, sorry, when is the furthest from the right, not fastest to the right. That's v. So when is moving furthest from the right? So we do need to find the velocity though. So we have 3t squared minus 30t plus 72. Factor out the 3, t squared minus 10t plus 24, which that factors into 3 times t minus 4 and t minus 6. Now, if you remember finding the max value on this, not only do we check the critical points, we also check the endpoints. So my interval has points 3 and 9. So I need to see, is it furthest at 3? Is it furthest at 4? Is it furthest at 6? Or is it furthest at 9? That's not too terribly hard to plug in, but I want to see if we can do this. I'm going to put this in here. Put the original function in here. So we have x cubed minus 15. So first, minus 15x squared plus 72x minus 9. All right. Now, let's see if mine will do this. There we go. On your calculator, if you go to table set, you should be able to change your table into ask. So that way you don't have to scroll down for whatever value. You can actually go to your table, type in what value you want to plug into the function, and it will spit it out to the y column. So let's go to table, so second table. So it's asking for 3, and there I got 99. We wanted 4, there I have 103, 6, 99 again, and 9, 153. So those are my values, 99, 103, 99, and 153. So where do I have where am I furthest to the right? At t equals 9 seconds. So again, on your calculator, if you go to table set, which should be above your window functions, so here somewhere. Yeah, table set, which is above the window button, so second window, you should be able to change your independent. You want to change your independent to ask. So yeah. All right. Now, part B says on that same interval, what is the particle's maximum speed? Now, if you remember, speed is what? Absolute value of velocity. Okay, and if I want to find the max speed, I need to find the derivative of velocity. So v prime, or a of t, the acceleration, would be 6t minus 30, which gives you t is equal to 5. So again, if I'm trying to find the max value, not only do I look at my critical point, but I also look at the endpoints. So I'm looking for v of 3, v of 5, and v of 9. Now, plugging those into the velocity function isn't really that bad because I can just plug them into here. 3 minus 4 is negative 1. 3 minus 6 is negative 3. So negative 1 times negative 3 gives me 3. And then times 3 gives me 9. 5 would give me 1 times negative 1 times 3, which is negative 3. And 9 would give me 5 times 3, which is 15, times 3, which is 45. All right. Now, because it's absolute value, yeah, I should make this the speed is positive 3, and this is what, centimeters per second? So centimeters per second. But it really doesn't make any difference because which one's my fastest? Yeah, 45 centimeters per second is the fastest. Now, we've done some concepts of finding, let's say, the equation of a tangent line using implicit differentiation. In those cases, we would plug in for both x and y. Okay, so we're going to do the same thing here when we have a implicit function, and when I want to find where the function is increasing or decreasing, again, I do need to find the derivative. There is some, like, one little thing I want to talk about. If you see this, I want you to know what it means. So we treat this like anything else. We're going to take the derivative like we normally take the derivative, but how we write the solution is going to be something you need to know. So consider the curve 3x cubed plus 3 equals natural log of 4y squared. At the point negative 1, 2 is the curve increasing or decreasing. Now, what that means is we need to find dy dx. Okay, that's what we're going to find. So take the derivative 3x squared. 3x squared gives me what? 9. Sorry, 3x cubed gives me 9x squared. Derivative 3 is 0. Now, the derivative of natural log of y of 4y squared is going to be 1 over 4y squared times 8y. So that's going to give me that 9. Well, don't forget this because people do this. Dy dx. Anytime I take the derivative of y, I have to include the dy dx. So that's going to give me 9x squared is equal to 8y over 4y squared dy dx, which gives me 9x squared is equal to 2 over y dy dx. So dy dx is equal to 9x squared y over 2. Now, when you plug in, we are going to plug in for both x and y. X is negative 1, so it gives me 9 times negative 1 squared times 1/2 over 2. That is going to give me 9 over 4. Oop, yeah, positive 9 over 4. We do know it's positive, but What we don't write is that dy dx is greater than 0. Okay, because we don't have that function notation like we would say before, because we'd say this is increasing. We do know this is increasing. All right. But before, our reasoning was like at f of -1 is greater than 0. But I don't have that way to write that. So the way you write this is you write the coordinate as a subscript for dy dx. So it is increasing because dy dx at -1 1/2 is greater than 0. So you write that coordinate as a subscript. And if I could make that tinier, I would. All right, similar setup. Consider the curve x squared minus 3 equals e to the y on the xy plane. At the point -2, 0, is the curve concave up or concave down? Which in this case, we need to find d squared y dx squared. So first, the derivative. We have 2x is equal to e to the y dy dx, which means dy dx is equal to 2x. Now I'm going to write this as e to the negative y, because I don't want to, I'd rather do a product rule than quotient rule. Okay, but if you want to do quotient rule, feel free to write that as 2x over e to the y. It's up to you. Now that means that d squared y dx squared, we're going to have to do product rule. So the derivative of 2x is 2 e to negative y plus 2x times derivative of e to the negative y, which is e to the negative y times -1 dy dx. So that is going to give me 2e to the negative y minus 2x e to the negative y times, we got to replace this with that, 2x, that should be y, e to the negative y. Which if you simplify, you get 2e to the negative y minus 4x squared e to the negative 2y. Now on the left is to plug in 0 for y and -2 in for x. So plugging in, we get 2e to the negative 0 minus 4 times -2 squared e to the -2 times 0. Now, anything to 0 power is just 1, so that's all just 1. So we get 2 minus 4 times 2, -2 squared is 4, so 2 minus 16, which is -14. So because it is negative, our answer is concave down, because d squared y dx squared at -2, 0 is less than 0. Now, nice what about number 3 is all the work is kind of done for us, because they gave us the derivative and the second derivative. Okay? And when you look at the question, it says consider the curve y cubed minus y equals x squared. So they, again, that's nice enough. They give us dy dx and d squared y dx squared. What they want to know is the point 0, 1 a relative min, relative max, or neither? Now, if you remember finding that, we could use the first derivative test But in order to do the first derivative test, I would have to plug in points around the value I have. And how do I plug in points around 0, 1? Like what points would you use? You can't, because you have to do almost like a circle around it. Okay. So it's so much easier just to do the second derivative test, which means plug this both into the first derivative, which you have, and the second derivative, which you have. All right. So we plug it into the first derivative because we do need to know if it is equal to 0. If we plug that in and get 0, we do know it's a relative extrema. And if we plug it into the second derivative and get it negative, we know it's concave down, so it's a max. Or if we get positive, it's concave up, which makes it a minimum. So we're just going to plug this into both. So we are going to find first dy dx at 0, 1. So plug that in here. We have 2 times 0 over 3 times 1 squared minus 1. Now, it doesn't really make a difference what the denominator is because 2 times 0 is 0. So therefore, it is a local extrema because dy dx at 0, 1 is equal to 0. Second part, we plug this into d squared y dx squared at 0, 1. And that gives you 2 over 3 times 1 squared minus 1 minus 24x squared y over 3y. Oh, so I'm actually plugging in values, sorry. 0 squared times 1 over 3 times 1 squared minus 1 squared. Again, the nice thing is this whole thing is just 0. So 1 squared is 1, 3 times 1 is 3, 3 minus 1 is 2. So we get a positive 1. Now, because this is positive, it is concave up, okay, which makes this a minimum value. So we have a minimum at 0, 1 because dy dx at 0, 1 is equal to 0, and d squared y dx squared at 0, 1 is greater than 0. And that is it for chapter 5. So 9 weeks, 5 chapters we've covered. Yeah. So